We're carrying on with our quantitative tools in chemistry. What we're going to talk about in this video are measures of concentrations of a solution. A concentration is a measure of how much material you have in a certain amount of solution. There are different concentration units, but the one we're going to focus on is called molarity. And your textbook calls it capital C for molarity. I guess that's because it's a concentration. The definition of molarity is that it's moles of solute per liter of solution. It's liters of solution, not liters of solvent. There are other concentration units that might care about how much solvent you use, but we really don't care. You're going to make up solutions of no molarity in the lab using this piece of glassware called a volumetric flask. And somebody hasn't used this one correctly because they've overshot the mark. What I see on this is a white line etched right there. So what you're supposed to do is put your solute in the bottom, add solvent and mix it all up, and then carefully, a little bit at a time, drop-wise, get it so that the bottom of the meniscus is sitting right on that mark. So then we will know what the volume of the solution is. That will be written on the flask. I think this is a 100 milliliter flask. So the beautiful thing about using this measure of concentration is that what I have here is a quantity written in terms of units of something per something else. Excuse me. Moles per liter. When we learned dimensional analysis, we saw that when we had units of something per something else, we could use that as a conversion factor. Molarity to me is just a conversion factor that allows you to relate moles of solute and volume of solution. That's going to be handy because moles is going to be a very central concept for us. If I knew the volume of the solution that I measured out, I could use the molarity to find out how many moles of solute there is. But let's not get too far ahead of ourselves. Let's work with just the definition of molarity. Here's the question. I want to know the molarity of a solution containing 5.12 grams of ammonium sulfate in 250 milliliters of solution, and I want to know the concentrations of ammonium and sulfate ions in the solution. So remember, as always, if you can solve this problem before I do, so much the better. The other thing I'm going to do before I set you loose to solve it for yourself is I'm also going to remind you that if you don't see the answer obviously, this might be a good place to practice making a map. That's what I'm going to do. But for now, I'm going to suggest that you solve the problem as far as you can by yourself. Pause the video. All right, I'm back. And if you didn't get all the way ahead of me, remember that you can always pause the video at any point once you get an inspiration. Here I go. I'm going to make a map to solve this problem. I always start at the end of the map. What is the question part of the question? And in this question, I want to know the molarity of the solution. So that's what I'm going to put in the box at the end of my map. And what I'm going to do is play the little game called What Do You Need to Know That? I like to play that as simply and literally as possible. I will play that by definition if I can. The definition of molarity is moles of solute, which is in this case ammonium sulfate. And the other thing I need to know is liters of solution. All right, let's see if we know that. I don't know moles of solute yet, but do I know the liters of solution? Yeah, I do. Well, okay, it's given as milliliters, and in the early days of this course, I would have encouraged you to use an explicit calculation to switch milliliters to liters. But at this point, I trust that if you just want to tell me that's 0.2500 liters, you can go ahead and do that. You use your best judgment and I'll use mine as I look at your work. Okay, so the only thing I have left to find now, I need to know how many moles of solute. What do I need to know that? Well, if you're inspired, keep working backwards. But just to demonstrate the flexible problem solving, I'll say I'm not inspired and we'll start at the other end. What I know, what I'm given, is how many grams of solute. That's here. So, got to stay loose and flexible. Maybe I'll work from the back, maybe I'll work from the front. If I knew how to convert grams to moles, I'd have this done. Do I know a conversion factor? Grams per mole. Molar mass. Yeah, I know how to do that using the molar mass. So I think this is the important part of the problem. I think your ability to produce a plan like this is what we're really after here. Now that I have that plan, I can go ahead and solve the problem, and now it's just a math problem. Okay, so the first thing my map says I want to calculate is moles of solute, and I'm going to lay that out even more carefully than before. I'm going to use the letter N. That stands for moles. N is the variable name and MOL is the unit, just like M is the unit for mass, and M is the variable for mass, and grams is the unit. So I want to know how many moles of solute. Now to find that from the mass, I'm going to need the molar mass. And to know the molar mass, I'm going to need to know the formula. So that's okay. We've learned that skill before. I expect you're going to be able to come up with the formula of ammonium sulfate. And now the question gives me 1.2 grams of ammonium sulfate. And I need a conversion factor that will get rid of grams and get moles. I'm being really explicit here. I'm saying grams of what and moles of what, because in this problem we have more than one thing. We've got the solute and we've got the solution. And I want to be as crystal clear for myself as I can be so I don't get snarled up. All right, units go first, then I know what numbers. Moles per gram, grams per mole, molar mass, mass of 1 mole. So now I need to tap out on my calculator what the molar mass of ammonium sulfate is. You don't have to show me your work for that. I trust that you can tap that out. I got 132.2 grams per mole. Grams in the numerator cancels grams in the denominator, and I'm left with moles of ammonium sulfate. Woohoo! So I'm going to tap that out on my calculator, 5.12 divided by 132.2, and I'm going to store that in memory 1 so that I don't get round off error later. I'm going to report it to the 3 significant figures I'm allowed, 0.0387 moles. You could, at this intermediate stage, report more than enough significant figures, but if you report fewer than enough, you will have lost information. That's a problem. All right, the map tells me to do that as my first step. So now I am here in my map and I can't get lost because my map tells me what to do next. I'm going to calculate the molarity. Now, a common way to express molarity is to write the name of the substance in square brackets. Those square brackets mean the molarity of. And I'm going to do that by definition. Molarity is moles of solute per liter of solution. Per means divided by. And it's got to be in liters. So I've got the unrounded value in my calculator divided by 0.2500 to the 3 significant figures I'm allowed. That is 0.155 moles per liter. Another way to say moles per liter, we often say capital M for molar. So I can say equivalently 0.155 moles per liter or 0.155 molar ammonium sulfate. Either is fine, don't need both. So I've come a long way along here, and now I want to make sure I've answered every part of the question. I have found the concentration of ammonium sulfate, but the second part of the question wants to know the concentrations of ammonium and sulfate ions. So let's continue on the next slide. I want to know the concentration of ammonium ions. Well, how will I find that? Ammonium sulfate, if you check your solubility rules, is soluble in water. So for every formula unit of ammonium sulfate I get, when it dissolves, I end up with 2 ammonium ions in solution. So that's going to give me a conversion factor. I knew that I had 0.155 molar ammonium sulfate, but I need a conversion factor to get me just ammonium and get rid of ammonium sulfate. Oops, that's a 4. And the equation below says that I get 2 ammoniums for every ammonium sulfate. Ammonium sulfate in the numerator cancels ammonium sulfate in the denominator. I've got my unrounded value for the concentration already in my calculator display. Multiply it by 2. 0.310 molar ammonium. Now, the first time I showed you this, as I often do, I made it really explicit. I showed that conversion factor. If you feel comfortable just looking at the formula of ammonium sulfate and saying there are 2 ammoniums for every 1 ammonium sulfate, I would accept if you just told me there are 0.31 molar ammonium. Last part of the question, what's the concentration of sulfate ion? Let's try it that gut way for this one. You could use a conversion factor just like I did at the top of the slide there. But what I can see is that I get 1 sulfate for every ammonium sulfate. Since it's a 1-to-1 ratio, the concentration of sulfate is 0.155 molar, just like the concentration of ammonium sulfate was. So far, so good. Let's try another question here. I'm going to take some 2.50 molar copper 2 nitrate and use it to make 500 milliliters of 0.1 molar copper nitrate. To solve this problem, I need a good visualization of what's actually happening here. I'm taking a more concentrated solution and turning it into a solution of lower concentration. The way I'm going to do it is that I'm going to do a dilution of the original solution. There's a picture on the bottom that shows you how you would do this. So I've got an original solution, I'll call that solution number 1, of a high concentration. I transfer some of that into the second flask, but just some of it. And then I make it up to the mark with water. And you can see that my new solution, solution 2, is less concentrated than the original one because the color is lighter. So that's how we're going to do a dilution in the lab. How do we handle it in terms of a calculation? Another strategy I'm going to throw in that you might like, you can use, you don't have to. I find that when I have multiple things going on, I like to draw pictures that I label with the quantities. So the question says I start with 2.50 molar, and I'm going to turn it into 500 milliliters of 0.100 molar. I'm going to transfer some of this over there and add some water, and that's how I'm going to make my new solution. That's really handy. The two solutions have two different concentrations, but now I won't get confused which is which. All right, there is a central idea that's going to guide all our dilution calculations. It turns out that the moles of solute transferred from the first solution has to be the same as the moles of solute in the new dilute solution. And that's because all of the solute in flask number 2 came from flask number 1. The volume of the solution was increased by the water, but that didn't add any more solute. So the moles that came from number 1 ended up in number 2. Let's see if we can solve a problem with that equality. Now, which one am I going to start with? Am I going to start with solution number 1, or am I going to start with solution number 2? Well, I know more about solution 2, the dilute solution. So let me first calculate how many moles of solute are in the dilute solution. I don't want to get confused. I just want a few words here and there to guide me. I want to know how many moles of solute there are in the dilute solution. All right. We had some copper 2 nitrate. We had, in this dilute solution, 500 milliliters of 0.1 molar. Here it might be a good choice to remind you that molar, capital M, is the same as moles per liter, which is something with units of something over something else. That's a conversion factor. I want to find moles. I already have moles per liter. The way to get moles by itself would be to multiply by the volume of the solution. That's what I'm going to do. Okay, so I've got 0.100 moles per liter and 500 milliliters. Well, watch your unit. This tells you that you first have to convert that volume into liters from milliliters. Liters cancels out, and I am left with 0.0500 moles in the dilute solution. All right, so now we're ready to look at the more concentrated original solution. The moles that end up in the dilute solution is the same as the number of moles I transferred from the concentrated solution. And what do I want to know about the concentrated solution? I want to know how much or what volume I would have to transfer. Okay, I want to know the volume that I want to transfer. And those units are liters. So let's see what we've got here. I know how many moles, and I'm going to have to multiply by a conversion factor that gets rid of moles and gives me liters. Gotta love that dimensional analysis. We've got a brand new kind of problem, but we don't need any new skills. All right, the units go first. Where do I get the numbers? liters per mole, moles per liter. Ah, that's molarity. In the previous slide, we saw that we had 2.50 moles per liter, 2.50 moles per 1 liter. Moles in the numerator cancels moles in the denominator. 0.05 divided by 2.5 to the 3 significant figures I'm allowed is 0.0200 liters, which is a perfectly fine answer, or it might be more meaningful to express it in milliliters. That would be 20.0 milliliters. So we would transfer 20.0 milliliters from the original solution into the 500 milliliter flask and dilute it to the mark with deionized water. We needed no new thinking skills to do this. We know how to work dimensional analysis. We just learned a new conversion factor in this section. Molarity is moles per liter. But some of you might have learned to handle dilution in another way. Remember, our central idea for dilution is that the moles transferred from the concentrated solution is the same as the moles of solute in dilute solution. And let's remind ourselves how we calculated the moles. Moles is molarity times volume. Moles is molarity times volume. Now the dilute solution we labeled was 2, so we'll call that C2V2. Similarly, the moles transferred concentration versus volume from the original concentrated solution. So you may have seen a relationship like that before. Some books show it C1V1 equals C2V2. Other books show M1V1 equals M2V2, M for molarity instead of C for molarity, just depending on the book. Are you allowed to use this formula? You are allowed to use anything that's true. I just showed you in the previous example that you don't need to memorize it and remember it wrong. You have the power to think it through, but you can use this shortcut because you know where it comes from. Let me tell you that this equation applies only to dilution. It is dangerous to memorize it and misapply it. I won't tell you what I've seen in my time. Just remember, this is only true for dilutions. So one last problem to cement that understanding. Here's a new problem. I'm going to mix equal volumes of 0.2 molar HCl in water. What is the new concentration? As always, at any point in this problem, it would be good if you could pause the video and finish it for yourself. I'll just leave that to your discretion and continue on myself. Now, one strategy I showed you in the last problem that I really like is making little pictures that I can label with the quantities to visualize what's going on. So I start with 0.2 molar HCl, and I'm going to put some of it in a new flask, and I'm going to dilute it with some water. And what I want to know is what's the concentration in the second flask. C1 is 0.200 molar, C2, we don't know. That's our unknown. Now I recognize this is a dilution. My new concentration will be less than my old one because I'm adding water. And I showed you the shortcut before, C1V1 equals C2V2. Now, where you go from here is up to you. You can put the numerical values in first and then rearrange, but I think it's more elegant to rearrange it first. I want to solve for C2. So that is C1V1 over V2. Now, Ready to put the values in. C1 is 0.200 molar. But what's V1? I don't know. I'll just label the amount that got transferred as V1. Now there's no number there, but that worries me more than you do. Because here's the beautiful thing. This worked out to be a ratio of volumes. All I care about is about the ratio. So when I don't know what a number is, I just put the variable in and hope a miracle happens. And I promise you that it will. Now that's V1. What is V2? The key is that it said we added equal amounts of HCl and water. So I added V1 of the acid and V1 of water. So V2 in this flask is V1 plus V1, or 2 V1s. I promised you to have faith and then a miracle would happen. V1 in the numerator cancels V1 in the denominator, and my new concentration is 1/2 of 0.200 molar. I don't even need a calculator, that's 0.100 molar. Ta-da! The new concentration is half the original concentration. Now you may not have done dilutions in biology yet, but you will see this. What we did here is called a twofold dilution. My new volume is twice the old one, so my new concentration, we proved, is half the old one. I could do a tenfold dilution if my new volume was 10 times my initial volume. Then my new concentration would be 1/10 the original solution. But enough of that for now. You can see that as long as you had faith that a miracle was going to happen, you could solve this problem using C1V1 equals C2V2, and that will cover your butt for this time. All right, friends, that ends this chapter. I will meet you in chapter 4.